In this video, we'll be looking at an example that I would argue is the most difficult example of all volume by attachment problems. Now, it says evaluate the volume generated by attaching equilateral triangles parallel to the x-axis to the region bounded by y equals negative x plus 3 and y equals x and the x-axis. So, first off, I'm going to need to figure out what the area of an equilateral triangle is. Keep in mind that every equilateral triangle should have three different sides, or I should say that differently, that they have three same sides. And I've got to find the area of any equilateral triangle. So I'm going to label this side as S appropriately because S is what we generally attach to those objects. Now the height here is a unique thing. Notice that the area of any triangle is 1/2 base times height. In this case it's 1/2 times S. We know the base here is a length of S. But the height is what we're going to have to figure out. And again, that's that length right there. Well, if you recall a bit of trigonometry, we know that this is a perpendicular bisector, which means that this length here to here is S, but this length from here to here is 1/2 S. So making note of that, this being a right triangle, I know that 1/2 S squared plus H squared equals to S squared. Again, this being a hypotenuse of this interior triangle. Keep in mind we're still trying to find the area of the big triangle, but we're just using this to find the height. So if I solve this equation, I should have 1/4 S squared plus H squared equals to S squared. I will go ahead and again solve for H in terms of S, this giving me the height in respect to the variable of S. I will then subtract 1/4 S squared, giving me H squared is equal to 3/4 S squared. And then I can square root both sides, giving me plus or minus the square root of 3 over 2 S. Keep in mind that I did that very quickly. The square root of 3 is the square root of 3, the square root of 4 is 2, and the square root of S squared is S. You'll also note that I've put a plus or minus here, but in most cases for application problems, we will ignore the negative case. So that right there is the height of any equilateral triangle, which tells me then if I plug this back in up here to the area of any triangle, I have 1/2 times the base times the height being the square root of 3 over 2 times S. If I were to simplify this, I would end up with S squared multiplied by the square root of 3 over 4. And again, S times S is S squared, 2 times 2 in the denominator is 4, and 1 times radical 3 is that radical 3. So this right here is the formula for the area of an equilateral triangle. We no longer need to do this setup. Every time that I ask you to find the area of an equilateral triangle, you can simply tell me that the formula will be square root of 3 over 4 times S squared. That is the formula for evaluating the area of an equilateral triangle. So now that I've identified that, the next step I would argue is for us to actually graph this object and view it to see what the region is that we're playing with. So I'm going to go ahead and do that right here. We're looking at y equals negative x plus 3, so 1, 2, 3. It should be somewhere up here, and it should be a negative x. So there's my line. The next one is y equals x, so that means that line is going to pass through here like this. Okay? And then the x-axis, which is right here. So it's very clear that the object that we're playing with is this one here. Notice how, again, I'm drawing those lines horizontally because we're attaching the equilateral triangles to this object parallel to the x-axis. So if I were to redraw this object, I'm going to go ahead and draw it a little bit larger. There's the triangle. It's the same triangle there. I'm going to attempt to attach equilateral triangles, which means that these triangles are perfectly the same length here, here, and here. So every single one of these that I do, it's going to be exactly, again, the same triangle all the way through. So again, this should build some kind of triangular prism. So the idea is then that I have to integrate in respect to y, because one more time, we're cutting this horizontally, so it should be cut in terms of y, such that I'm going to have a function on top and a function on bottom. And the area formula that I'm playing with, one more time, is this formula up here, such that I figure out what that side length is. That side length is, one more time, the distance from here to this point over here. Again, we're cutting this way, so this function is the one that's on top, and this function is the one that's on the bottom. Now you'll notice that this is the negative linear function, so y equals to, it was negative x plus 3. That's my top function. And my bottom function is simply y equals to x. Because again, I'm cutting this direction, so it cuts through this function first and this function second. So, now that I know which function's on top, which function's on bottom, I simply plug them into the s formula. Because again, that's what we label this thing here as, it's a distance of s. So the distance of s is going to be negative x plus 3 minus x, which is simply just going to be a negative 2x plus 3. But what do we do with that function of s? Well, again, I'm starting at y equals 0, and I'm going to the intersection point of those two functions. So again, I'd set these two things equal to each other and solve. So that would be x is equal to a negative x plus 3, and I'm going to add this and get x is equal to 3 divided by 2. So unfortunately, it's a fraction, but that doesn't stop us from setting up this area integral such that we end up with a volume. So the volume is equal to the integral from 0 to 3 halves, again, that point right there, the y value. Oh, wait, this is an x value. So we should make sure that we plug this back in over here to get the y value, which you'll notice right here, x and y are the same value. So I just want to make sure that I emphasize that detail, is that when I set these two functions equal to each other, we end up with the appropriate setup that we're supposed to have. Secondly, this s doesn't actually apply. It doesn't apply because this is all in terms of x, and therefore I need this all in terms of y. So this one's fine, but this one needs to be transitioned to x equals, which is simply nothing more than me adding the x over and subtracting the y over. So I end up negative y plus 3. So the functions don't actually change in regards to those situations, which means that, again, this one still being on top, this one still being on the bottom, I'll end up with something very similar to this, but actually in terms of y. So s is equal to a negative y plus 3 minus 1, giving me, again, the exact same equation, just in terms of y. So my area formula is, again, square root of 3. I'm going to go ahead and write this very carefully here. It is the integral of y equals 0 to 3 halves, all in terms of y, of radical 3 over 4 times s squared, and s being a negative 2y plus 3 in terms of y. That is the setup for the integral of my volume. I can take this radical 3 over 4 and pull it outside, and then I can square this function here. I'm going to end up with a square root of 3 divided by 4, y equals 0 to 3 halves, of a positive 4y squared minus 12y plus 9 dy. And again, I integrate each piece separately. I plug in 3 halves as the upper bound, I plug in 0 as the lower bound, I subtract those two values overall, and then multiply that whole thing by radical 3 over 4. So this is the setup for evaluating equilateral triangles. Again, this is the area for equilateral triangles. Cut horizontally, because we've attached these equilateral triangles in respect to the x-axis, or parallel to the x-axis. Therefore, my integral has to be in terms of y, and everything is in terms of y, to simplify and evaluate.